to do with Euler's identity. Can you believe it? Doesn't seem connected, huh? I'm telling you, math is one of the most creative endeavors in the world. Let me prove it for you. Okay, so I'm going to prove this one, the mother of them all. It's the mother of them all because from it comes all the other identities that, for example, double angle identities, power reduction identities, sums to powers, etc., etc. Double angle identities. This is the mother of them all. We've already proven it this way, but by letting a triangle fall. But today I wanted to prove it using the famous Euler's identity. And just keep in mind, you don't have to watch this. In fact, I don't have to do this. Sometimes, dancers, they dance for money. And sometimes dancers just dance because they love to dance. Math teachers are the same way. Sometimes we prove things just for the paycheck, just for the money. And sometimes we prove things just for the love of proving things. So I'm just telling you off the bat, this one is not for the money. This is just because I love this proof so much. This one's on the house. Alright? So in order to prove that, here's what we need: a couple ingredients. First ingredient that we need, of course, is Euler's identity. Okay, we've already learned that. We already practiced it a lot. I'm going to put a little check mark on that. No, I'm going to put a little yellow check mark on that. FOIL, this is from algebra. First, outer, inner. I'm going to put a check mark on that. Really, the only other ingredient that we need is something that I called the guessing game. So let's learn that one. It'll take us about 20 seconds to learn the guessing game. I won't even tell you what the rules are. We'll just start playing it. The guessing game goes like this. I write a complex number like 3 plus 5i. And I tell you it's equal to some other number. It's equal to blank plus blank I. And in that blank I put x and k. And I try to ask you, can you guess? That's why this is called the guessing game. The guessing game. Can you guess what x is? And can you guess what k is? Assuming these are real numbers, here's the way the guessing game goes. If you have a complex number that's equal to some other complex number and they're both written in standard form, then the real parts have to be equal and the complex parts have to be equal. So therefore, here's a good guess for you. X would have to be equal to the real part 3. The one that's next to the y, the one that's next to the I would have to be the imaginary part. That would be the k. It has to be equal to the 5. That's how the guessing game goes. You get it? It's pretty easy, huh? Let's try it again. Let's try it again. Let's clone this guy. But then let's make this stuff disappear. And let's clone this one so we can try it again. And so I've got the guessing game again here. Suppose I had 3 halves I plus 4 is equal to a hair plus a chair I. Ooh, take that. Can you guess what the hair is equal to? And can you guess what the chair is equal to? Let me tell you how the guessing game goes. You assume that they're written in standard form, so then this part, which doesn't have an I, must be equal to this part, which doesn't have an I. So the hair must be equal to the 4, just like that. And the imaginary part, which is the chair and the I, must be equal to the imaginary part here. So therefore the H must be equal to 3 halves. That's how the guessing game goes. So hair is equal to 4, H is equal to 3 halves. You get it? I think you could use one more. Let's play the guessing game here. Suppose you had 4 plus the square root of 3 times I is equal to no. No. Plus the square root of 3 plus 7 times... No. Sorry. I'm getting nervous all of a sudden. Plus 1 over the square root of 2 is equal to a plus a bi. Can you guess what the a is, and can you guess what the b is? It's just called the guessing game. Assuming a and b are real numbers, and these are complex numbers written in standard form, which piece goes with which? The a. Just think about it. The a, does it have an a? No. You've got two pieces here. This one has an I and this one has an I. The a does not have an I, so therefore the a must match up with this one. And so the b, which is the imaginary coefficient, must match up with that. So therefore you can conclude that, here's the conclusion, your a is equal to 1 plus the square root of 2, and your b is equal to 4 plus the square root of 3. You get it? That's called the guessing game. Pretty easy, huh? Alright, I'll stop there. These are the three ingredients. Euler's identity, check. FOIL, check. The guessing game, check. Okay, two complex numbers are equal if and only if their corresponding real parts are equal and the corresponding imaginary parts are equal. That's it. That's all you need to prove the famous mother of them all. Can you believe it? Amazing, huh? I'm gonna do it. I'm not gonna do it for the money. This is just for the love of proving things. Watch this. In fact, I never told you guys this before, but you know that sheet with the famous identities? I don't have any of them memorized. Not even the mother of them all. Every time I need to remember it, all I do is prove it using Euler. Let me tell you how it goes. This is what I do. Every time I gotta remember that, I go like this. E to the x. What would Euler say about e to the xi? Well, Euler would say that that's equal to cosine x plus I times sine x, right? What would Euler say about e to the negative iy? Well, the negative can go as a coefficient, as it can go with a y, so it would say that this is equal to cosine of negative y plus I sine of negative y. Yes or no? Stop me if I'm lying. That's exactly what Euler's identity would say. In fact, you could clean this one up. It would say that this is, what's cosine of a negative angle? Cosine doesn't care if the angles are positive or negatives because cosine is an even function. Sine does, so that the negative could come right through the sine function, and that would give you that much, right? Still though, that doesn't tell you anything, but wait, there's more. What would happen if you multiply the left sides, these two? Well, you'd get something like this, e to the xi times e to the I times negative y. And on the right hand side, you multiply these, so you'd have cosine x plus I sine x times cosine y minus I sine y. Is that right? Here, I'll show you what I did. I multiply this one and this one. That's that one and that one. And on the right hand side, I multiply that one and that one. That's those two right there. And I'm multiplying in the regular mundane world, and I'm also multiplying in Euler's utopia world. And they have to be equal because they're the same numbers, just written in different ways, written in the regular world and written in the Euler world. But wait, there's more. How do you multiply numbers that have the same base but different exponents? You add them together. So this would be e. That would be e that's not blue. That would be yellow e. E to the I times x minus y. Because you would just add the exponents, x plus a negative y. On the other hand, we know how to do FOIL, right? You're not afraid to do FOIL on this, are you? No, you're not afraid. This is a paper tiger. Cosine times cosine, this would be cosine x times cosine y. That's the first. Outer would be minus I sine y cosine x, plus the inner, that would be I sine x cosine y. That's the inner, cosine y sine x. I. Then the last ones would be minus I square sine x sine y. Is that right? Whoa, let me see. Actually, this cleans up nicely. But wait, there's more. This cleans up nicely because I square is -1. So -1 times negative, this would be a positive. So this means that e to the I x minus y is equal to cosine x cosine y plus sine x sine y. That's this piece added with that piece. That's this whole piece. I still got to do these other ones over here, the ones that have I.